Here. I've been on the quest for the ultimate Kelvin connection. My interest in very low ohms measurement requires that, and just been looking for the ultimate probe that will work in all situations. So we started with the obvious, just 4 separate connections of a Kelvin connection. Kelvin connection is where you source your current through the resistance, black leads, and independent leads are sensing the voltage drop across the resistor. This way, with 4 leads, you are not measuring the resistance of the leads taking the current to there, with such as a 2-wire measurement. So that's the whole purpose of a Kelvin connection, is to separate out the current sourcing and the voltage sensing. So this works, and it works well, but 4 connections for everything is a real pain in the neck. So I said, okay, let's make some Siamese connectors. I like these Pomona connectors, the J-hook style connectors, because they certainly don't fall off and they're a good connection. But this requires too much space between the 2 connections. The source is the black, the sense is the red, and so it's not real convenient to get on places, and it's a little bit clunky on the end. Now I think it's better than the Mueller clip, which really these don't stay on very well. They're kind of finicky on staying on, depending on how your leads lay and everything. And they do work. They do keep your source and sense separate all the way to the device under test, and you can get on reasonably small areas and things, but still not happy with those. Another thing that is that's used is a probe, where you actually want to probe a point. Well, in theory, with a Kelvin connection, you can't do it with a probe, because a probe's a single point, and you actually have to have your 2 connections, your source and your sense, separate all the way to the device under test. So these are what Pomona / Fluke Kelvin probes. They do keep the source and sense leads separated all the way down to as close to the tip as possible, but you still have the resistance of this section of the tip on both sides added to your resistance measurement. So that might seem like, oh, who cares? But if you're measuring down into the low resistance range, where you're talking, micro ohms or tens of micro ohms. If we come here and measure this, if you look at this, we're talking about 122 micro ohms of resistance times 2, and I'm not even measuring the full distance that goes in there. So we're talking about 1/4 of a milliohm resistance just in the tips there. So yeah, they're better than nothing, but they're not really a true Kelvin probe. And we were measuring that with the probes that are my final design. These are Pomona pincers that have been modified to keep the 2 leads electrically isolated, so that source and sense are electrically separate on each side. So this video is going to cover how I designed and constructed these, and then on the next video we'll show additional parts of the system, where we show how there's a probe designed to connect with these. It's a true Kelvin probe that measures at a single point. And then also an additional add-on unit that allows you to connect whatever you want to the ends of these, any combinations of grips and things, because sometimes you want a gripper connection in one place, probe connection in another would be convenient. But typically, either plug in grippers or clips or a probe, you don't have a mixture, the ability to mix them. So this video is going to cover just the construction of how I made these, and then the next video will cover the remaining items. What about the Pomona gripper like this? Real convenient, gets into a lot more spaces, can grab the edge of a surface mount resistor, quite easily and one-hand operation, but there's one problem, and that's that the center conductor of it is all one piece, so that it wouldn't allow me to get two independent conductors down there, because one probe has to be the current source, the other has to be the voltage sense. So this needs to be split full length all the way down and have two conductors. So that's exactly what I'm doing. Here I have cut the clip end off because I need the beryllium copper spring type contact and the gold plating, and then I just surface ground the bend right here where it's folded to separate them into two individual contacts. Here's the pincher clip out of a Pomona pincher clip, and it's been cut off from its stem that goes out the back here, and since I'm making Kelvin clips, I need to have these independent. And right there where my pencil tip is, that's where it's actually folded over. It's 14 thousandths material, it's actually folded over there. So I'm going to grind off just that fold so that these two pieces are separate. And I'm just going to show a quick setup in the grinder how that was done. So here's two pieces of 20 thousandths spring steel that I have here to sandwich the piece in between, and then just a piece of scrap metal, round scrap metal, that sits on top, but the lines of flux of the chuck come up through and still pull that down. So that'll actually hold that piece to the chuck. The piece is beryllium copper. The pinchers are beryllium copper gold plated. So now this is all held with the magnet, and now we'll go ahead and grind that. So there it is, ground. We've ground the arch off there where it's folded. Now we're going to pop this off the chuck, turn the magnetic chuck off, lift our piece, get our tweezers, and now you can see that these are actually separate pieces. They're all ready to go. So now those pieces will get soldered separately into the two separate halves to keep the source and sense separate through the whole Pomona pincher clip. Now that I have those little spring clips, I need to have a means to connect them all the way to the back, keeping them electrically separated. So in the end of this brass piece that we're going to make, I have broached a rectangular hole that will accept the rectangular tang of what we just cut off. This is about 25 thousandths wide, about 14 thousandths thick on the one side. So we'll make this as a round piece, broach the hole, and then we will slit this full length with a 6 thousandths slitting saw to cut it into two pieces. And then we will insert a shim, Teflon shim in there, we can see there, that will keep it isolated in there. And here is the, if we look at the tip here, we'll see where we put the actual pincher tips in. There they are with that added, and those get soft silver soldered in. So this keeps electrical isolation. And then we put a piece of Teflon or FEP heat shrink over that to keep it solid as a unit. So now we have these electrically isolated all the way back, and then this, of course, at the end is the tab where we solder our two independent leads on. Another issue is that in the standard pincher there is a steel tube down in there that supports the spreading load of those pinchers. Basically, it's the bearing surface that the pinchers ride on to provide the closing action. Problem with that is that would short the two probes at that ring and not form a true Kelvin connection at the part. It would form a Kelvin connection at that ring. So that ring needs to get replaced with something non-conductive. Here's the nose clip that we've designed to be non-conductive and hold the gripper pieces. This is going to be made out of Torlon, and this diameter right here will be a press fit in the plastic just like it is now. A rectangular broached hole through, and the rest just shoulders on here on the plastic. So that's the piece that we will make, and we have to make a punch or a broach for this, and also a broach for the brass piece that the spring clips get soldered into. Here are the two broaches that I've made. Just ground them out of old broken taps. It's just a good source of high-speed steel. And this one on the left is for the small 27 thousandths by 34 thousandths rectangular hole. That is for the brass piece where the spring clips for the pincher clips go in, get soldered in. And then this one is for the plastic nose piece that the spring clips ride in. This one is 28 thousandths by 56 thousandths. And in the end of these is a spherical pocket that's ground with a diamond ball abrasive tool. Before I ground the squares on there, so I just stick it in the lathe with it spinning, take the ball tool in the center, keep it centered, and let it form a spherical pocket. That gives a positive cutting action. Maybe if I get up top here, you might be able to see the slight curvature that's in the end of these from this, where the spherical breaks out to the face. And then the big flat on one side is so that I can orient them and know which way they're indicated across that to line them up if I need to. So those will be used to broach those two pieces. Machining the Torlon nose caps for these. You see these are pretty small. It's only 80 thousandths in diameter. This diameter is 115. And there are a couple that are done with the first back operation. So we're turning this and this diameter, then parting them off, and we'll come back and do the chamfer, drill the hole, and put the broach in. I've already faced off the probe tip with the chamfer on. Now we're drilling the hole that goes in before we do the broach. Circuit board drill. Now we've got the hole in there before we do the broach. Here we're putting the bevels on the tips of the tip for the pinchers. You can see the flat on there, flat on the other side. We're milling those on, and then after we do this, we'll go line them up in lathe and broach the hole. Putting the support pin in the center, help to not crush the tube with the collet. Put it in. There we have the finished chamfer. Here's our probe tip with the hole drilled in it, the 30-degree bevel that's on two sides, and now we're aligning the bevel in the lathe by just turning the spindle with the brake on, and we're indicating across that flat with the indicator here a 50 millionths best test. And as you can see, as we traverse across here, we climb up on, we go across, and that's pretty close. It's within 50 millionths, but just by chance. Totally unnecessary for this, but that's how we line them up. And then the tool on this side is, get that thing to focus. The tool also has a flat here that I indicated in to get it true, so that this rectangle is aligned. So now I line the tool in this direction, back and forth, using my digital readout, and I get dead center, and I just plunge right in and take a cut, come out. I'm going to move over 1/1000th away from me and take a cut on one side, and then move 1/1000th the other direction from centered, take a cut on the other side, just because my tool was a little narrow in trial from what actually needed to be. So now that slot's 0.58 wide instead of 0.56. I'm turning the nose of the Pomona body to match the diameter of the Torlon tip that we made when it's pressed onto a pin, 80 thousandths pin. This is the same diameter as the neck of the Torlon pin we made. This is just so that when it's put together it's concentric and it will fit into our probe body. Doesn't take a lot off, it just makes it concentric to the ID and makes it at the same size in that press fit condition. Here I'm indicating in the rectangular punch, making sure that vertically and horizontally I get the same reading on all four flats, because that's important with something this small. Broaching the rectangular hole. There's the rectangular hole broached in the previously drilled hole. That's 145 thousandths deep. This is the drawing for the body that's going to hold the two independent pinchers that we removed from the original Pomona pinchers. We whacked these off and surface ground them to get them into two separate pieces. This is the body that's going to hold those two pieces, and it's going to get sawed in half once we're done machining it round. So the procedure on this is it's not the easiest thing in the world to turn a 50 thousandths diameter by 1 5/8" long piece in brass, and I'm going to use the what I call the poor man's screw machine method here, where we use the collet, we grab, having just a little bit sticking out, we turn, one cut, full depth, right on size, we come out, we back up, we grab with the collet again, come back in, cut, and we use large material. We use a material much larger than the piece in order to have support for that part that's sticking out of the collet. So we just migrate our way back, chuck, grab, turn, chuck, turn, chuck, turn, chuck, turn, until we've got what we're after. And that's a procedure we're using. And you can see in the end here, after the first operation, where I turn it, actually drill the hole, we have broached our very small rectangular hole that will be where those two Pomona grabber clips get soldered independently into each half after this is sawn in two pieces. Now that we have our turned piece with our broached hole in the end to receive the grippers, here's a blow-up of that where we have our 26 thousandths wide by 036, and then we're going to cut it in half with our 6 thousandths saw blade. We have our diameters turned for the full length of this. We have our 215 thousandths diameter here at the end. Now we're going to machine this flat section, which is actually forms these ears that are replicating the thin section of the original Pomona clip where it goes into the movable part. The original clip is 14 thousandths thick, but the actual injection molded slot's 20, so I'm beefing it up a little bit and so that it stays just a little bit firmer in there. So now we're going to set up on the mill to do the flats on here, this milling operation, and still holding similar to screw machine style where we're going to hold on to excess material on the back. We'll machine this part and then we'll end up parting this off in the lathe. Here's the setup in the CNC, and you can see in one vise I've got an indexer to do the positions, flipping it over to get the parts, both sides of the part exposed to machine it. And then here we have the original broach put into the hole temporarily to be able to indicate across it to rotationally align the part so that the rectangular hole is aligned with the flats that we machine on here. And this support block is here to the indicator pressure on that long extended piece would just bend that, so we have to support it while we're indicating across there. And I just manually move this in and out on the top of the vise to indicate that in, rotate it with my fingers as I close the collet chuck to get that to read a small number. So if I go across here and indicate across, we come up on, we traverse across. If I can do two things at once, camera in one hand and indicator in the other. You can see here that where we go across, and that's reasonably flat across there as we traverse across the flat. Keep in mind the divisions on this are 0 to 1 is 1/1000th of an inch. So those divisions are 50 millionths. So it looks like it's moving a lot, but it's a very fine indicator. I know this isn't a machining forum, but just a tip for young players. Whenever you have an end mill extended relatively long distance, and anytime you have reasonably small end mills where you're going to have a low chip load, a low number of thousandths per chip that you're loading, it's important to actually tap in with the collet nut, tap in the end mill to get it to run as true as possible, because if it doesn't run within a few tenths of running the same position per each tooth, then one tooth is going to be doing all the cutting. If this thing runs out, let's say 1,000th, and you're only taking 5/10 thousandths of an inch chip load per tooth, that one tooth is going to be doing all the work, and you're just not going to get as good a finish, and the cutter's not going to last as long. We're going to drill the 2 holes here for the 2 separate leads, and that 5 or 6 thousandths saw cut's going to go right down between the 2 of them. That's where our wires will go when these are separated. Now we're finally going to part this thing off from its body. There it is, parted off. Just cut the little tab off, this little tip. Just cut that off with a pair of flush cutters. So here's the 6 thousandths thick slitting saw, high-speed steel slitting saw, and it's 1 inch diameter. And then I've made a solid arbor to hold it, and it's just super glued onto the end of the arbor. High quality super glue, not your garden variety stuff, but Loctite, high strength, high temperature version. So that's what we're going to use to slit those things in half. Okay, now we're coming to the part where we're going to cut them in half. And there's a little fixture here where I have a 6 thousandths steel shim underneath this brass piece. The brass piece has a 50 thousandths high step, and it has a back wall for this 50 thousandths diameter of the part to actually get in. So get over here, back up a little bit, where you can see this end. There you go. So we're putting the part in, and we're holding the part just by this little tab on the end here, and the part is going to just be held in the whole thing is just held by this tab on the end, and all of the lateral and back force is held by this block. This block is held on by the it's bolted to my vise. I have tapped hold of my vise for this kind of situation. So that brass block is bolted on solid, and it's clamping down the 6 thousandths shim that's underneath it. So basically there's a 50 thousandths wide nest that keeps this thing centered, and I have the 6 thousandths slitting saw correctly sitting so it's right down the middle. Now one thing that's an important thing with slitting saws, especially when you get thin stuff and you have something like brass that can be kind of cantankerous as far as cutting. If you get a little burr on an edge of the cutter or whatever, it can be uncooperative and want to deform, and that 6 thousandths blade can just climb out of the cut and do all kinds of crazy things. So a little trick is to take about a 5 thousandths deep cut, in this case, full length, where just the teeth are just barely engaged, and it gives a slit that's centered. There's no forces trying to make the blade climb and do crazy things. You'd be amazed how far those blades can flex before they break. So what I did there was I just put a little cut in, full length, you can see the chips there, and now there's an actual groove in that piece that's right on the edge. Very hard to see even with the camera here. But what that'll do is that I go full depth now. Actually, I'm going all but full depth. I'm just leaving a little bit of web in the back so that this thing stays together and doesn't collapse onto the blade. When I take it out, I'll just be able to unfold it. So now I'm going to my reading on my digital of how deep I'm going. And now I'm just going to use some lubricant, and I'm just going to slowly feed through, going full depth all but on this. Since I'm climb milling, it's pushing the part into the fixture. I'm just sweeping the cutter to swish the little mini brass chips out. You don't want anything getting clogged. These are very fine teeth. They're actually not ideal for this long length of engaged cut, but it'll work. You can see the little chips, piles of chips piling up there. Get some more stuff here, lubricant. Now when I get to the end is actually thicker. So when you see me pause, I'm actually feeding a little bit deeper so I get completely through the tail end here where that little square is. it's actually thicker. So I'm going to be stopping here and feeding until I get clean through the part, another 12-15 thousandths. Then I'll saw through the rest of it. Come through, come out of the cut, get back, blow off all of our cutting junk, and pop open the vise. Remember, all we were grabbing by was, we literally were just holding that thing from skidding through there. Now, I get the whole thing back up so you can see the whole thing. Now I'm just going to unfold this. Remember I said there was a little web in the back? Well, that's all we had, was a little web in the back. Here's our two separate pieces, sawed precisely down the middle, and all we need is a little deburring on these, and these will be ready to go. Here's our half hole, that rectangular hole that we put in. There it is on the one half, and that's where the beryllium copper contact that we cut out of the original Pomona clip will solder in. So these are the pieces that have been sawed in half. You can see the rectangular cutout that's in there, and that rectangular cutout is going to receive the square. It's going to get soldered in like that. That's why we did all that work to get that in there. So to do that, put a little bit of this is soft silver solder. This is Stay Brite. So this is like 15,000 psi solder as opposed to lower strength solder. So this is strong stuff, but it's corrosive flux. And I'm just using a little piece of ceramic here to sit on, and a little three-legged stand for put some weight on it to be able to hold it still, and insert the rectangle into the end here, slide right in, and that butts up into the end of the hole, and we have our flux in. So now we're just going to heat it up. Don't need hardly any solder there, but we have to get it good and warm so that it flows all the way to the back. I'm holding it in, and there we go. Unweight this, and if we look at this, you can see that that's fully flowed around that piece. And then we will take this over to the ultrasonic. Just give it a dip in the ultrasonic while it's running to get all the junk off. Rinse in the sink, and we're ready to go. It's a better view of that rectangular hole. It's actually rectangular section in a round hole, so you can just see the corners there, but they do align the piece that goes in, and as far as the depth, and keeps it centered and aligned, and it's flush. So that's what we were trying to show in the other section of the video. Yes, my fingers are horrendously dirty. Get over it. That's machinist fingers. Here's 10 sets of the pincher leads done. There's the original Pomona clip soldered into the body that I made, and this heat shrinks just to keep them in mated pairs. Just kept the original bodies matched. And next we'll do the Teflon separator. Here I'm cutting the Teflon sheet, and just by trial and error, after a while you can get to where you can visually get your thickness that you're after, the width. I need to be roughly 50 thousandths, and so this stuff isn't all that expensive, so just kept measuring and trying and getting a visual lineup on the 50 thousandths wide. And those are the strips that will go in between the pieces to keep them electrically isolated. Cutting our heat shrink tubing at length, just using a little piece I made to go onto a pair of standard cutters, screw into the end of the rod. Standard clamp collar. You can set it with the calipers to your length. Here's the pieces with the heat shrink and the Teflon liner in. If we look here, we can see that we've got our Teflon insulators between there on that end, and then on this end we also have it, and it has to come all the way out to the end because as this thing closes it would short at the back edge here. There you go, you can get closer now. It would short at the back edge, so that Teflon has to sit all the way out to the tip. And then one of the problems is that I forgot, design wise, that we put the spring on, everything's fine, we were insulated on the inside diameter, but I forgot about the spring shorting right here. So I'm just going to have to cut a little washer that will protect that, keep that spring from touching and shorting the two conductors at the back instead of letting it be a true Kelvin connection at the front. So I needed the washer to insulate the spring from touching the two sides of the connector body. So method, this isn't anything rocket science, and it's not my idea, but just so that some people haven't seen it. So I need a 70 thousandths hole, and I want a 1/8 OD. So I have a standard pin punch set that has 1/8 diameter dowel pins it uses for punching the hole. So I drill the size hole I want, in this case 70 thousandths, and then I turn, you can either turn or grind the nose on the pin to form a punch with a pilot on it. And then you can just go down through and line up with one of the drilled holes. It's piloted. Just give it a wrap, pull it out. You can go to your next hole. Make sure you don't have a piece still stuck on the end of the punch. Oh, can't reach from that side. That's what was stopping me. I had to flip it over. I was running into the post. There. Up. Another one. Let's get some of these out of here. Push them out of the bottom. And there's all of our washers. Nice concentric. In close. Nice concentric washers, stamped. And you can do the same thing with brass, steel, whatever, but like I said, it's not a new idea, but some people might have not seen it. Using some custom cable here. It's got 26 gauge that's comprised of 65 strands of 44 tin copper with FEP insulation, and then it's also got a spiral braid shield and then a silicone jacket, so super flexible. Really nice stuff, and also small enough diameter to go in the clips properly. So this will make extremely nice leads. They won't fight you. Here's the cable soldered in. See our Teflon separator. Here's our two conductors, our red and black, and we will alternate those with, in this case, red on the left, black on the right. And then we will alternate on the other side. On the next clip it will be black on the left, red on the right, so that when you're holding two clips you have your source and sink are opposite hands of each other in case you need to align them in a particular way on your part. Otherwise you'd have to turn your clip around every time you wanted to do that. You'd have to have one facing one way and one the other. This way they can both be the same direction and have the source and sense in the opposite hands on each side. Here it is installed in the clip. There's brass pieces are in their grooves, the silicone's in its socket there for the wire. It's a nice snug fit in this, so this is going to work excellent. And then on this side you can see where the brass is here. The brass is exposed, and that's where our washer is going to go on. Here's the plastic washers down there that insulates the end of the spring from shorting out the two conductors. Here's the monoclip head that's been closed up now that we've got it all soldered up, and in here we've got our plastic washer, springs on. You may be wondering why the brass was such a small diameter, only 50 thousandths in diameter. Why I couldn't make it bigger, and that's because I initially took the thinnest wall heat shrink that I could find to determine what the outside diameter would be that would still clear this spring. So I tried it on test pins, gauge pins, and shrunk this heat shrink on and figured out that the diameter has to be 50 thousandths in order for this spring to just clear. So that's what determined that 50 thousandths diameter of the brass that was holding the pieces. Seems a little strange that it would need to be that small, but I couldn't find any thinner wall heat shrink. So we have to machine the tips of the pomona body right here to remove the length on the end of this, shorten it so that it accommodates the shoulder length on from here to here on the new polyimide tips that I made. These are going to get pressed into the end of the body here. But I have to machine this, so how do I hold on to this thing? I can't just grab it back here in a collet. It's not rigid enough to do that. So a trick for machining this is to just make a little collet adapter where this has been relieved in the back to allow the gripping length to be such that the short length of diameter that I'm going to grip on right here, from here to here where I had previously turned it, as you saw in the video, is going to get inserted in there. So just insert that in, put that in here, slide it out, then we stick this in a 3/4 collet, and I can machine the end of this off precisely and chamfer it and everything, rotating, and then remove it. And the fact that it's larger in diameter here than the body back here allows me to slip it into the collet. Even if I had well, I do have a collet that is this correct size for this 115 thousandths diameter, but the collet's grip length is longer than this, so I wouldn't be able to get to it because this wouldn't stick out of the collet. The grip length is too long and it would ride on the taper and prevent it from poking out too far. So just a little tip for the machinists or wannabe machinists that are watching the forum. So we have to machine some off the end of these. I have my calipers set in incremental mode, and I have them zeroed at the length that I'm after. So there's 68.5 thousandths, 68 thousandths on the overall length of this. So now I will simply put this in the collet adapter that you saw earlier, and we will touch off on the lathe and take 68 thousandths off the end of this. So now we're going in the collet. We're going to pick up on the end of the part with the eye loop, and I get the eye loop in there, and the plastic is too spongy to touch with the end of the tool to see where I am, so I need to do it visually just with the magnifier to see where we are. So now I've got the digital, zero it out, tell it how much I'm taking off, and that's what we'll do. Now I'm going to come in part way, just taking it off, turning the whole thing off, but then I'm going to back out the end, come in and cut into the center so that I don't end up with a horrendous burr on the outside. And I just come in with a little tool and chamfer the inside, and we're done. There's the piece, the bird, pop that out, and we're ready to go put the Torlon tip in. So we have to insert our Torlon tip into the body that we machined, and it needs to be aligned to the grippers, and it just so happens that the parting line here that we can see on there on both sides is my visual reference for aligning this. So I'm going to put this in, get it started. There we go. Get it started enough that I can then twist it around visually, and I'm aligning this rotationally in here before I push it all the way in, so that it's visually parallel to the parting line of the gripper. So that's aligned. So now I'm just going to push this in without influencing it, without crushing the air. Nice press fit. So there's our 80 thousandths set up there. Then we have our gripper that we're going to insert in. And it's ready to go in, springs all loaded and everything, and this just going to clip in. Now it's captive, and you can see our grip action, and we have it just recessed so it's just below. It just goes in just below, and these actually touch. These will actually grab zero thickness as they go back in there. So that's all ready to rip. Here's the other end of two Kelvin clip leads that are connected to the DIN connector for the LOM 510 micro ohm meter. The resistor, the surface mount resistor, is 100K. Those are between source and sense, so that when you're in dry contact mode, that the open circuit voltage is limited, so that it doesn't go crazy until both sides of the probe are connected. We've got the shield there, got a little tubular piece on the pins to enable the full shield diameter to get in there. Here's the connector body with the inner pieces in, strain reliefs on over the adhesive heat shrink, and now we're going to put on the metal cap. So they're really quite nicely made connectors. They're injection, or not injection molded, but die cast material, and very nicely done. Here we are. We're all good, strain relieved. So now we're ready to put our rest of our connector parts back on, and oddly enough, I actually remembered to put them on. And even stranger is, I actually even put them on in the right direction. This is actually a modified connector. I couldn't find any that were meant for just plug-in only, that had decent contacts, silver contacts, and so I just used this one, and I just machined the nose of it to suit what I was after. So this thread's on. It's in the ballpark here. There's a little tab on the back connector, that the rubber that seats in there to keep it from spinning, and that's it. That connector is running into the shell, makes this firm, and that's all she wrote. Strain relieved. We got the heat shrink, sticky heat shrink on the back section here just for a short length, so that this still has some room for strain relief, and that's ready to plug into the LOM 510 micro ohm meter. And of course on the other end is our custom Kelvin pinchers, where those two connectors on each side are independent. Here's a set of the leads. I made up with short 18-inch leads with the new Kelvin pinchers, and this is a connector box from a set of tweezers for the DE5000, so I just used those as my connection. And in the DE5000, the source and sense are different. The two black leads are the source, red leads are the sense, and the shield is to the guard. I'm not sure if it's actually a driven true guard or whether it's just a shield. If it was a guard, it would actually be driven to the potential of the sense leads to eliminate leakage, but I'm not sure. I haven't measured. Actually, I don't know enough about it to measure it. But remember, I'm a machinist, so But other than that, this would be a nice set of leads now for the E5000, and these are a lot handier than the alligator clips to be able to get on smaller things, and also for resistance. The D5000 or any half-decent LCR meter does a real good job on low ohms. The next video is going to cover the design and construction of the probe attachment, and this is going to be a true Kelvin probe where the source and sense are separate all the way down to about a 10,000th diameter tip, so you'll be able to probe like on 8,000th legs of ICs or whatever. And there's actually a slit down through the center of that keeps them isolated all the way to the tip. So you'll see the whole construction of that, plus the universal attachment for attaching anything to the end of the Kelvin clips.